Why are creatures where they are? We obviously don't live on a planet where life forms are spread in a homogeneous manner. Different types of animals and plants have distributions and concentrations. Basically, all creatures have a geographical range, some broad, some narrow. For example, this is a pebble toad, Oreopharynella nigra. It lives specifically on a type of mountain called a Tepuy in Venezuela, steep-sided, flat-topped mountains that rise majestically out of the jungle, like islands in the sky. This toad is what we call an endemic species. It is only found in this specific highland area of Venezuela. Incidentally, this little toad has developed an interesting defence strategy against anything that might fancy toad for dinner. If it feels threatened, it can tuck itself into a ball and throw itself down a hillside like a rolling stone. I must admit, I've been in some parties when I wished I could have done that. The opposite of an endemic species is a cosmopolitan species. For an example, well, just go look in a mirror. From the steaming tropics to the ice and snow of the Arctic, from the deepest jungles to the tops of mountains and baking deserts, you'll find Homo sapiens. Since we evolved in Africa around 200,000 years ago, we have spread to every corner of the globe and are certainly the most cosmopolitan primate on Earth today, although I'm quite sure that our primate cousins would claim that that was nothing to be really proud about. On a very broad scale though, life can be divided up into several biogeographical provinces or ecozones. These are geographical areas of the world that have characteristic communities of species. For example, I am currently in the Nearctic ecozone that includes North America and Greenland. Europe, Asia and North Africa are in the Palearctic. Others include the Neotropic, Afrotropic, Indo-Malaya, Australasia and Antarctic at the bottom of the world. Ecozones can also be recognised from Earth's geological past, but in this case we have to consider the additional complication that wandering continents add to the story. Some things we need to consider then. First is the manner in which diversity changes very broadly across the planet. To do that, although it might sound a little off topic, I also need you to think about how the planet's magnetic field intersects with the ground. It has been suggested that the movement of liquid metal in the outer core around the solid metal inner core, due to convection and the Coriolis effect of the spinning Earth, produces electric currents which, in turn, generate Earth's magnetic field. At a very simple level though, you can imagine the Earth to be like a giant bar magnet with lines of force running from the North Pole to the South. Just like a bar magnet, our planet, the magnetic field is inclined towards the vertical at the poles, and at the equator it will be more parallel to the surface of the ground. Practically, this means magnetic inclination and latitude are linked. This signal, as we've seen, can be locked into certain fine-grained sediments and basalt lava when iron-rich minerals take up the magnetic inclination at the time of their formation. So, if you can record the inclination of the magnetic field in the rocks, you can also estimate the paleolatitude of the rock at the time of its formation. There is a relationship between latitude and the diversity of organisms too. The diversity of organisms is highest at the equator and drops off towards the poles. Have a look at this diagram adapted from a 2006 paper written by my colleague Paul Smith at the University of British Columbia. It shows a clear relationship between increasing magnetic inclination of magnetic minerals in rocks and decreasing diversity of organisms, in this case bivalves. Both the magnetic inclination and the diversity data provide potentially useful information about where on the surface of the planet, in a latitudinal sense, a particular rock was formed. These are important clues that we can use when trying to recreate the history and movement of areas of our restless planet. The second point we need to consider, though, is the concept of barriers to the migration of species. On land, barriers could be an inland sea, like existed in North America during the late Cretaceous period. They could be mountains or even a dense forest. In the oceans, barriers can include swift currents or deeper parts of the ocean where food resources may be limited and can be as much of a barrier to shallow marine creatures as a mountain is on land. Barriers could also be due to different temperature and climatic regimes. Of course, as paleontologists, we are also concerned with a dimension beyond the current geographic one. We want to know what happens to the distribution of plants and animals over time, what we call dispersal biogeography. One of the first people to consider such migrations was American paleontologist George Gaylord Simpson. Simpson imagined species originating at a central location and then dispersing over time. Dispersal would vary depending on the ease of movement of the creatures. For example, if you consider mammals at the taxonomic level of orders, the largest groupings of the class Mammalia across North America, 100% of orders found in New York State are also found in Oregon. The degree of similarity will decrease as you consider the finer taxonomic resolutions, like the smaller groupings of family, genus and species. But in general, you can regard North America as being fairly homogeneous. This is what Simpson referred to as a corridor, a place where creatures can mix fairly easily. Other migration routes are more selective, allowing for the passage of only a restricted selection of creatures. For example, during the last ice age, the Bering Strait became dry land as sea levels fell. This allowed migration of animals between Asia and North America, but possibly, due to climatic factors, not all animals exploited this new opportunity. Creatures that would migrate include the mammoths and bison that would spread from Europe to North America, and horses and camels that would migrate from North America to Europe and beyond. Simpson termed this type of feature that imparts a selectivity than what can migrate a filter bridge. Possibly the most famous example of a filter bridge comes from the development of the Isthmus of Panama, the thin ribbon of east-west trending land that today connects North and Central America with South America. At about 3 million years ago, volcanic islands formed by the subduction of the Cocos Plate below the Caribbean Plate were starting to be connected as sediments filled in the gaps in between them. As a result of this, a migration of faunas occurred between North America, which eventually was linked up with tectonic plates forming Central America, and South America, which up until that point had been pretty well geographically isolated. To use Simpson's evocative term, South America, until linked with the rest of the world, has spent considerable time in splendid isolation. Because of this isolation, a whole range of exotic marsupials had evolved in South America, like Thylacus milus, a marsupial predator resembling a saber-toothed cat. And there was fast-footed camel-like Marcochinia, and the Glyptodon, not a marsupial but a relative of the armadillo, with adults about the size of a VW beetle. Overall, there would be a greater net migration of creatures from the north into the south, an event we call the Great American Biotic Interchange. But this was no simple mixing of species, as many of those exotic creatures in South America would be driven into extinction. But why mostly the South American forms? The answer may, in part, be due to climate. In general, during this time, much of South America was very warm and moist all year round. When large terrestrial animals of the South American fauna moved north across the land bridge and into North America, they rapidly encountered more extreme variations in climate. This effectively placed a lid on most of the southern critters' migration, but not on the dispersal of the hardier North American animals, who are able to cross this filter bridge and start to replace those wonderful and now regrettably extinct beasts of South America. The third dispersal mechanism Simpson termed sweepstakes. This describes migration due to the relatively rare but still important effect that plain dumb luck has in the movement of some organisms from one place to another. For example, creatures that are rafted to oceanic islands, perhaps after major floods when large mats of vegetation are swept from large continental river systems out into sea. This is possibly the manner in which the ancestor of the Galapagos marine iguana landed on the island about 8 million years ago. Simpson also recognised that dispersal and associated isolation is a powerful force in evolution. The isolation of South America, for example, had permitted the development of its unique fauna. The same is true for the weird and beautifully wonderful fauna of present-day Australia. Something to consider, though, about the development of land bridges is that although they permit the mixing of some groups of creatures, they may also act as barriers to others. For example, the formation of the Panama Isthmus separated two oceans that were once linked through the Caribbean, an event called the Great Schism. Populations that were once in contact were now isolated on either side of this newly in place landmass. This may account for the diversification of mollusks on both sides of the isthmus, due to the isolation of populations and their independent evolution in these new marine environments. This evolution of new species may have been caused by the mollusks on the Caribbean side having to adapt to more nutrient-poor conditions once the nutrient-rich water of the deep Pacific was now blocked. As paleontologists and geologists, though, we have to account for another factor when considering the distribution of species, for it is not only creatures that migrate, continents do too. Simpson, however, was no fan of the idea of drifting continents, so his view of the dispersal of organisms through time was essentially a static one, with continents and the ocean basins occupying their current locations for over hundreds of millions of years. But with the dawn of plate tectonics and the dynamic movements of continents over time, a whole new way of looking at the dispersal of fossil species came to light. One of those concepts was developed by Malcolm McKenna, a curator of vertebrate paleontology at the American Museum of Natural History in New York City. He called his idea Noah's Arks, and it describes how isolated landmasses could drift across an ocean and run aground on another continent, releasing any unique endemic species that had evolved on the ark during its isolation. India may have played just such an ark role. About 170 million years ago, India and Madagascar were locked in the middle of Gondwanaland, a southern landmass comprising South America, Africa, India, Madagascar, Antarctica and Australia. By 150 million years ago, Madagascar, India, Antarctica and Australia split from Africa and were separated by a narrow ocean. And by 105 million years ago, India and Madagascar had split from Antarctica and were drifting northwards. Here at 66 million years ago, at the time of the death of the dinosaurs, India had left Madagascar behind and was zipping in glorious isolation northwards on a collision course with the underbelly of Asia. By the early Eocene, groups of mammals like the even-toed ungulates, which includes modern animals such as pigs, giraffes and hippos, and odd-toed ungulates such as modern horses, tapirs and rhinos, suddenly appear in Asia. It's been proposed that it is from animals like this, Cambrotherium thilwesi, found recently by researchers from Johns Hopkins University, that all the even and odd-toed ungulates would evolve, carried by Noah's Ark India across the ocean, evolving in isolation till they, and possibly other mammals, were released when India finally docked with Asia. This is an intriguing possibility, although it has been suggested from research in amber and arthropods that these deposits may have formed after docking had occurred. As such, the Gondwana-India ark fauna, if they exist, may have to be sought from older deposits. But for the rest of this episode, I'd like to consider another type of geological ship, a Viking funeral ship. For just as Viking chieftains were sent to Valhalla on a ship that was set afire and pushed out to sea, so too can exotic fossil assemblages be set adrift on continents and continental fragments to beach thousands of miles away in a completely different part of the world. In doing so, they leave a story of their origin and their journey through time. So for the rest of the episode, let's ask, who were the fossils in Alfred Wegener's jigsaw puzzle? How can fossils time the closing of an ocean? And what are exotic terrains, and how do fossils trace the dance of continental fragments through time? The story of the German climate scientist Alfred Wegener, who challenged the static view of continents, has been told many times. To summarise though, Wegener amassed a wealth of data to suggest that the continents were once joined. These included similarities of the stratigraphic record on distant continents, evidence of glaciations that once covered a united supercontinent, and the apparent fit of coastlines on either side of the Atlantic. In 1915, he would propose the existence of a supercontinent called Pangaea that existed over 250 million years ago. Accordingly, the current continents represent the fragments of that united landmass that have subsequently drifted to their current locations. But perhaps some of his most compelling evidence for continental drift came from fossils, many of whose current distribution is puzzling in the context of a static planet. Consider, for example, Cyanonathus, a metre-long predator from the early Middle Triassic period. Cyanonathus is a member of a group of reptiles, the synapsids, that were probably very diverse during the Permian period, but took a severe hammering at the Permo-Triassic extinction event 252 million years ago. The survival of this group of reptiles is important to our own story too, as synapsid reptiles would give rise to the true mammals later in the Triassic period. It is the paleogeographical distribution of Cyanonathus that is interesting for our story though. Fossils have been found in the Karoo Basin of South Africa and Lesotho, and also in China. Nothing unusual there. It could have walked to those locations based on earlier views of static, immobile continents. But what about specimens found in Argentina? And now also from the Fromau Formation in Antarctica. That would be an impossible journey, even for such a powerful land creature as Cyanonathus. It is the same story for another synapsid, but this time a herbivore, Lystrosaurus, that evolved in the Permian but would become one of the most common vertebrate elements in the early Triassic faunas, and possibly prey for carnivores like Cyanonathus. Once again, it is the distribution of these animals that is of interest. Like Cyanonathus, Lystrosaurus has now been found in South Africa, Antarctica, China, and also India. Physiologically, neither of these creatures were adapted to swimming, so how could it be that they could be found on such distant continents separated by enormous oceans? The same is true for this creature, Mesosaurus, a Permian marine reptile about 3.3 meters long. It had a streamlined body and webbed feet, long narrow jaws and nostrils on the top of its head, probably swimming a bit like a crocodile by undulations of its long flexible tail. Like crocodiles though, it is unlikely that this creature was able to cross a major ocean. This makes its distribution on either side of the Atlantic in Africa and South America once again difficult to explain with a static Earth. And famously, there is Glossopteris, an extinct order of woody, tree-like seed ferns. Some reach 30 meters tall, with tongue-shaped leaves and associations with other floral elements such as horsetails and lycopods. Glossopteris evolved during the early Permian and became the overwhelmingly dominant species in the southern hemisphere during that time, where it was an important coal producer. Fossils of Glossopteris are found in Australia, South Africa, South America, Madagascar, India and Antarctica. Certainly a bizarrely wide distribution for any plant with the continents fixed in their current locations. These distributions, of course, only make sense once the continents are drawn back together, as you see here, the distribution of plants and animals now makes sense in terms of a geographical range across a large landmass. No one here is having to leap across oceans. This might sound like a bit of a slam dunk for continental drift. There's a problem though, a problem with the mechanism Wegener proposed to explain how the continents drifted. He suggested that the gravitational pull of the Sun and Moon and the spin of the Earth were dragging the continents around the planet. This was a very difficult pill for many scientists to swallow, as these forces are nowhere near what would be needed to move a continent. For this reason, and probably because he was challenging the received view of the old school, the hypothesis of drifting continents was largely ridiculed. The distribution of Wegener's fossils were explained away by the rafting of creatures, the presence of land bridges, or island hopping. It is difficult, though, to see how these mechanisms could operate over large oceans and how they could account for the distribution of so many fossil species. Eventually, the idea of drifting continents would be revived, but this time with the more plausible mechanism of seafloor spreading. Scientists like Harry Hess, Marie Tharp, Bruce Hazen and J. Tuzo Wilson would pull together information from ocean floor topography, seismic records and ocean floor magnetism to give us the theory of plate tectonics that we are familiar with today. It would be J. Tuzo Wilson who, on the basis of fossils like trilobites, brachiopods and graptolites, and his understanding of plate tectonic motions, would propose the existence of a large ocean in the northern hemisphere. He called this ocean the Proto-Atlantic and claimed that this ocean, later called Iapetus, closed during the Silurian and Devonian periods. To illustrate what Professor Wilson noticed about these fossils that would allow him to make such a brave prediction, let's travel to Canada, and in particular to the beautiful province of Newfoundland. Newfoundland lies off the coast of eastern Canada along the Atlantic Ocean and has a long and fascinating geological history. Of particular interest to our story are the Cambrian trilobites and the fact that, although of the same geological age, trilobites of western Newfoundland are different from those of eastern Newfoundland. The association of fossils in the west are called the Laurentian fauna, and those in the east are termed the Avalonian fauna. What is particularly odd is that the western Newfoundland Laurentian faunas have more in common with those of Scotland, northwestern Ireland and most of the rest of North America. By contrast, the eastern Newfoundland Avalon faunas that also occur in New Brunswick, Nova Scotia and Massachusetts share more fossil biogeographical connections with most of Europe, including England, Wales and Southeast Ireland. Before the advent of plate tectonics, this mismatch of trilobite faunas across the Atlantic was explained away by a bunch of geological and oceanographic gymnastics, including the existence of land barriers or really odd oceanic currents. But in a plate tectonic context, what it tells us is that Newfoundland is a sutured landmass. In other words, the two halves were once associated with different continents on either side of an ancient ocean that subsequently had been brought together and fused by plate tectonics. You can see the two halves here around 455 million years ago during the Ordovician, when eastern and western Newfoundland were separated by the Iapetus Ocean. The fossils are different because the western and eastern parts of Newfoundland were in different climatic zones during the Cambrian, on opposite sides of the Iapetus Ocean, with the ocean being sufficiently wide at that point to even prevent the mixing of marine species. The two trilobite faunas were brought together when the ocean closed. Where the two faunas meet represents the line along which the eastern Laurentian and the western Avalonian terrains were sutured together in what is today Newfoundland. When the Atlantic Ocean opened up, splitting the continents apart again, fragments of the Avalonian or Laurentian faunas were stranded on either side of the ocean. The collision of these continents, though, would create an enormous mountain chain, not unlike the Alps today, the much reduced fragments of which now exist in the highly eroded mountains of Scotland and the modern Appalachians. Fossils will not only uncover the presence of this ancient ocean, though, but would also help document its closure over time. It is thought that the Iapetus Ocean opened in the late Precambrian as an older supercontinent called Rodinia fragmented. British paleontologists like Stuart McKerrow and L.R.M. Cox would record changing faunas on either side of the Iapetus Ocean as this body of water narrowed. McKerrow and Cox found that faunas in Europe and North America were most different during the Cambrian and Ordovician, with only planktonic species like the Cambrian graptolite Dictyonema and the Ordovician form Didymographus bifidus being found on both sides of the ocean. Graptolites are colonies of little filter-feeding zooids that floated in the ocean and would have probably been able to mix freely across a large body of water like this. It is estimated at its widest point, Iapetus would be about 4,000 kilometres wide. As the ocean started to close and the distance between North America and Europe was reduced, creatures that had a planktonic larval stage, like trilobites and brachiopods, started to mix on either side, first at the level of genera, but later with particular species found on either side of the ocean. In addition to planktonic forms, nectonic, free-swimming organisms like the conodonts were also starting to make the crossing. As the ocean narrowed even more, less mobile forms were able to make it across, like tiny benthic ostracods, which are now able to just crawl from one side to the other. And by the end of the Devonian, the Iapetus Ocean was sufficiently narrow that even freshwater fish were similar in Western Europe and Eastern North America. This classic study shows how fossil funeral ships like the Avalonian and Laurentian trilobites on Newfoundland alerted geologists to the possibility of a lost ancient ocean, and then how, charting the dispersal of fossil communities across that ocean, it closed over time. And if you travel to the Isle of Man, off the northwest coast of England, you can go and visit where continents actually touched, now represented by the Narrabul Fault, all that remains of the once mighty Iapetus Ocean and the mountains that form by this closure. To me, this is pure geological poetry. Since the early days of plate tectonics, when the theory was just starting to make sense of so many puzzling features of paleontology and geology, our understanding of the complexity of the wandering continents has increased considerably. One of the ways our understanding has become more complex is in an appreciation of what are called exotic terrains. In addition to large continental masses lumbering around the planet, it was realised that small fragments of continents have also been rifting off larger parent bodies and zipping around the Earth like marbles, colliding with other areas, potentially thousands of miles away from where they originated. A classic example of this comes from Western North America, the North American Cordillera. Exotic fragments can generally be recognised by geologists in the field when mapping highlights major fault zones that represent lines of disjunction between the rock unit to either side. The exotic blocks themselves differ dramatically from the surrounding geology, like a jigsaw piece in the wrong place, with paleontology and sometimes paleomagnetic inclination very different from the surrounding geology, suggesting a more exotic, perhaps significantly distant origin. More than 50 exotic terrains have been identified in the Western North American Cordillera. They may constitute about 70% of the total region, producing what could only be called a tectonic collage. Fragments can be composed of ancient volcanic islands, oceanic ridges, various ocean floor volcanic features, and fragments of other continents. This so-called accretion tectonics is probably a common process through geological time, but is most easily recognised in relatively recent rocks with relatively less deformation, where traces of those fragments can still be uncovered. In considering how fossils help us in understanding of the movement of terrains, we need to appreciate how populations of species of organisms differ in relation to the geographic distance between them, or in other words, the further away they are from their original source, the more dissimilar they become. The similarity between populations can be calculated using the Simpson coefficient, in which the higher the coefficient, the greater the similarity between two populations. For example, consider the Simpson coefficient recorded for either side of the Pacific and Atlantic from the Jurassic period to the present day. Basically, as the Pacific shrinks due to the widening of the Atlantic Ocean, there is an increasing similarity between Pacific species and an increasing dissimilarity between Atlantic species. Just what you would expect, right? This is a powerful tool when attempting to reconstruct the movement of terrains. As we mentioned earlier, diversity gradients and paleomagnetism are useful tools in determining the ancient latitude of a particular terrain occupied, but there is an obvious drawback. We have no idea about the longitude of the terrain, and this is where fossils and similarity coefficients come into play. A good example of the use of fossils in this way comes from Paul Smith's work on a number of exotic terrains in Western Canada, and in particular two specific terrains called Wrangellia and Stickinia. Paul was able to compare the similarity of certain endemic Jurassic ammonites and bivalves found in these terrains versus species of the same groups found on the North American mainland. The comparisons were made by examining fossil assemblages, in which he was able to determine that the Wrangellia terrain and Stickinia terrain, during their drift across the ancient Pacific Ocean, maintained a fairly close biogeographical association, not separated by much distance, as suggested by the similarity of the fossil invertebrate assemblages from both terrains. It was also possible to determine that the terrains were in the eastern Pacific during the early Jurassic due to the presence of North and South American taxa present in the assemblages. Paul could also establish the relative positions of the terrains, with Wrangellia being outboard of Stickinia, as Stickinia shows a higher similarity with the North American craton than does Wrangellia, and due to the minor presence of Western Pacific fossil species on Wrangellia that are absent on Stickinia. These and other observations have permitted a fairly detailed accounting of these two blocks through this time interval and beyond. Other studies, like Paul's, have helped us unravel a picture of what today is a really complicated geology, the product of collisions between various bits and pieces zooming across the Pacific and colliding with the main North American continental landmass. I think Wegener would have been astounded at the level of detail we have now uncovered about the movement of the fractured surface of our planet. The history of the changing geography of planet Earth is still being uncovered though, aided by our friends, the wandering fossils.